So today, week 25, we're getting into some more advanced topics now, which, at least for this class, you're not going to see this on Mathcounts, but you are going to see it when you go to high school. So, better early than late, I guess. I don't know if that's a real saying, but today we're going to be doing logs. And next week, we're going to do trigonometry, which has more relevance to the Mathcounts if you're still focusing on that. Okay, so let's jump right in. So we're going to review our exponent rules because logs have a lot to do with exponents. Define what a log is. I'm going to look at log rules, which are similar to our exponent rules. So first review our exponent rules. If we remember that, like, I think maybe in the beginning of the semester, I quickly looked over this. Exponent rules are the product rule. If you multiply two exponents, you add the powers. Divide, you subtract the powers. You take a power to a power, you multiply the power. So all of those rules are in that table. I'm sure all of you should be very familiar with this already. So not to take too long on this, but it's very similar to our log rules. So quick look at this. So now I'm going to introduce what I like to call the pyramid of operators. This is not a real thing. This is something that I made up. Okay, so in the pyramid of operators, we have two pyramids. The first pyramid is the one on the left. Okay, at the bottom is addition. Above it, multiplication. And above multiplication, you got powers. Why did I do this way? Because multiplication is repeated addition. Right? If you add something by itself a lot of times, that's the same thing as multiplying, right? So multiplication is repeated addition, and taking something to an exponent is repeated multiplication, right? So this is how the pyramid works for the left side, and the opposite side is subtraction, division, and roots, like square roots, cube roots, all that. So you can see that these two kind of like undo each other. These two undo each other, and these two undo each other. Okay, and we have these two pyramids. And if we look at how these pyramids relate to the exponent rules, if we have an operator outside, like multiplication, when it goes into the exponents, it goes down the pyramid one level. Does it make sense? Because look, for the product rule, for example, if we have a to the x times a to the y, we know that we have to add the exponents. So outside of the exponents, we're not doing anything to the powers themselves at this point. Outside of like if you define like taking something in power as a function, outside of this power, we have a multiplication. But if we put that inside the powers, we do addition. Quotient rule, if we have a to the x divided by a to the y, when it goes into the powers, when we have a to the x blank y, the division, it moves down a level on the pyramid. So division right here, it moves down to get to minus. Power rule, let's look at that one. When we take a to the x to the y, we're taking a power to a power. If we put all of that inside the exponent at this point, a to the x something with y, then it moves down a level. We had powers here, it moves down a level to multiplication, a times y. And that's what's going on there. So the exponent rules, whenever we have the basic pattern we see here is that for any operation outside of the exponents, let's say it's division, when that goes into the exponents, we move down a level. Let me say again, let's say outside of the exponents, we have this operator, division. When it goes into the exponents, we take the operator that's one level below on the pyramid, a to the x minus 1. Okay? That's the reason why. That's the reason you can't do anything like There's no rule for a to the x plus a to the y. There's no rule for that because if you have addition, you can't go any more down. There's no operator below that. So you don't have a rule for a to the x plus a to the y. So whenever you have an operator outside the exponents, when it goes into the exponents, you got to take the operator that's one level below. So that's how the pyramid of operators applies to our exponents. We'll look back to that very soon with our log rules. Okay. But first, we got to define what the log even is, right? So defining the log. So here's the basic definition. For numbers a, b, and c, such that a to the power of b equals c. For example, we could have 3 to the power of 2 equals 9, right? We could rewrite this in log form. We rewrite this. Log AC equals b. Okay, so in this case, we could turn this into log form by doing log 3 9 equals 2. The log doesn't do anything. The log is just a function. It's like it's just like something taken to a power. It's the same thing. The log, they're not variables or anything. It's just something we it's almost like division and multiplication, right? The plus sign is not a variable. It's not an actual quantity. It's just something that we know that it does something, right? So the log, it just does something. It's not really there multiplying to anything. So that's how we rewrite something in log form. So why is log form even necessary? It's because if you look at this, we had a to the b equals c here. It basically takes the power out of it. Now b is on its own. Okay? Which is really important because if we have some kind of equation where we have, let's 3 to the x equals 10, we can turn this into log form, right? Right now we don't have any form, any way to calculate what x could be here in this equation. But if we turn this into log form, we can take that out of the power. We can take that out of the exponent. So x would be by itself because it's the power, and that equals to log base 3 times 10. So if we were to calculate this with a calculator, that would give us x. So that's what logs are for. Logs are for finding the exponents. It's for taking the exponent out, so we have the exponent by itself on one side. Because right now we don't have any way of calculating anything when the exponent is inside, when the variable is inside the exponent. So the log takes it out for us. So what a log does is it undoes an exponent. It undoes it. It's like the opposite of exponents. Okay? Like plus and minus, those are opposites. Times and divide, those are opposites. So logs undo exponents. So what that means is if we had log a to the, so let's say we had log a to the b. If we take the power of that, it undoes it. This a to the power and log base a, they cancel each other out. So all we have is b. Okay. So if we take, so that's basically what's going on here. Just like if I add 3 and then minus 3, it does nothing to change my number, right? If I had like b plus 3 minus 3, I get b. Same thing goes here. If we originally had a log, which is here, and we took the power to that log, it undoes the log, so all we have left is b. Same thing if we were to do it here. If we had a power and we took the log and applied it to the power, this log base a and this a to the power would cancel out, and all we have left is b. So logs undo exponents. They're the opposite of exponents. So you might be wondering why I refer to this one as a base a, and that's just the way we call this log. The small number at the bottom is the base, and I'm not sure what this is called, but it's the bigger number. So what it does, so when I look at this log function in words, I'm asking myself, b is the power needed to get a to c. What does that mean here? If I wanted to find the quantity, the value of log to 8. How do I find that value? I could turn it into exponent form. That's why I could do it. Let's say this is x. Then I could turn it into exponent form, 2 to the x equals 8. And I could just observe what this means, and x would be 3. Alternately, we could directly think about what this log means. The log means the power, the number that we have on the other side, is the power we need to apply to this base to get to 8. So what power do we need to put onto 2 to get to 8? 3, right? We need 3 2s to get to 8. So that's the idea here. Any questions? So that's what the log means. If you take an algebra 2, this should be mostly review. We'll get into some more advanced problems later on the homework, so no worries if you've already learned this. We got these problems. They should not take too long. So these are valid equations. These are true equations, like 2 to the third equals 8. But convert them into log form. So I don't think you'll be able to chat me these. So we'll quickly go through these, and then maybe in 2 minutes, we'll check our answers. So you guys don't need to chat it to me. Just have the answer by your side. So that's the way we can get it most quickly, because it takes more time for you to write it down in the chat than it does to actually do it. Okay, so you don't need to chat it to me. All right, so quickly speeding through these answers. The way I like to do it is, first we have whatever going on in the powers on the left. And what we do is we just swap these two. Log 2, 8 equals 3. So let's say in here, the 2 is on the left, the 3 is in the middle, the 8 is on the right. Now we swap the 8 and 3, the 2 is on the left, the 8 is in the middle, the 3 is on the right. Okay, so that's my little trick of converting it. But that's the reason that works is because you're just following the rule here where a to the b equals c is the same thing as log a c equals b. And we can check this by asking ourselves what the log even means. The log means the value of this number is what power does 2 need to get to 8? What power do we need to apply to 2 to get to 8? And it's 3. And that makes sense. Okay, so let's speed through the rest of these. Log 4, 16 equals 2. Log 16, 4 equals 1/2. Log 3, 1/3 equals -1. So I'm just swapping the middle and the right. But this only works if the power is on the left here. All right, so make sure you understand that. This one is a little tricky. It's not a power, it's a square, it's a cube root. So what do we do here? Well, remember that cube roots, if we apply a cube root, that's the same thing as raising it to the 1/3 power. If you remember your exponent rule. So 20, this is the same thing as 27 to the 1/3 equals 3. And in log form, we just swap the numbers again. And that's it. So the last one is log of 1/3, 9 equals -2. Those are all the answers. Any questions here? Cool. Now let's do the opposite direction. Convert these logs into exponents. And one quick thing I forgot to mention is sometimes you're going to see, as you see on your calculator, is that there's no base operator. You cannot define your base on the calculator. You see here, my calculator has a log. And if you can see in this log, it has no base. When it has no base, we automatically assume it's 10. Okay. When it has no base, it's 10. The log, just no base, is the same thing as log base 10 of x. Okay. Just a quick side note. Okay, so let's quickly go through these answers. If we did the swapping from exponent to log, we do the same swapping again. Swap these. So 5 squared is 25. That is true. X to the z is y. 3 to the -1 is 1/3. And for this one, remember there's no base here. We assume it is 10. It's not we assume, it is 10. That's how the math people have decided to say this. Okay, so it is 10. So there's an invisible 10 in there. So you can write it in if you want. And if we swap again, 10 squared is 100. Okay, so now we're going to solve these equations with logs in them. Okay. So I'll give you some time to work on these. Same rules apply. Sometimes it's easier to put it into exponent form first. So since these are solving equations, you can chat me your answers for these. So let me quickly go over the first one to give you an idea of how to do these. So for the first one, doesn't look like we can solve this right at the bat. We could guess what number to the 1/2 power gets us to 27. That's what the log is telling us, but we could turn this into a power form, exponent form. So if we swap these, we get x to the 1/2 power is 27. How do we undo this 1/2 power to get to x by its own? That's what we're doing all the time when we solve equations. We just want to have x by itself. How do we do this? Well, we take this to the second power, so these 1/2 and 2 cancel each other out. Same thing here. Since it's an equation, these cancel, so x equals 27 squared. You could calculate that, but not necessary here. So that's how you do the first one. I'll give you some time to do the rest of them. All right. So let's look at these. Second one, let's convert that into exponent form by swapping it again. 2 to the x to the 50th is 2 to the 100. X to the 50th, remember our multiplication rules. Since that's a power to a power, our exponent rules tell us that we got to do this to the x times 50. And here, we have the exponent, the powers have to be the same because the bases are the same, right? So 50x is 100. X equals 2. All right? So that was that one. Let's look at next two. Log 9x to the 1 equals 1/3. We swap them again. 9 to the 1/3 equals x. That's pretty easy. That's our answer. All you have to do is swap it. Okay. Last one's a bit tricky. We'll swap it again. 2x to the 3rd power. And I'm going to put that all in parentheses because the whole base is getting put to the 3rd power equals x squared. All right. So now we can distribute this exponent. 8x cubed equals x squared. And cancel this out. X equals 1/8. Maybe you're wondering, well, there was another solution here, right? If I didn't cancel this, say log x to the 3rd, I could factor this instead of canceling, right? If I factored this equation to get what I want, the first solution is what I got, x equals 1/8. Oh, x squared could also equal to 0. Oh, is 0 a solution? No, we can't consider 0 a solution because if we plug 0 back in, what happens? We got log 0, 0 equals 3. We swap this, what do we have? 0 to the 3rd power equals 0. That's right, but the problem is that 0 to the any power could equal 0. 0 to the 5 is also 0. And in terms of math rules, that's not allowed. So what's going on here is that we can't have 0 as this number. Because any other number to any power would never get you to 0. Right? If you had 5x equals 0, I challenge you to find the value of x that would get you to 0. You can't. There wouldn't be a value of x. So in terms of log rules, we can't have 0 in there. Okay? So we only consider the x equals 1/8 solution. Any questions? So do be careful, guys. If someone asks you to solve this equation, 0 would be a solution. Just this equation by itself. Yes, 0 is a solution. Good. But the problem is this equation came from this one, and 0 doesn't work here, so you can't use 0 in the end. Okay, let's move on. Okay, so now we have log rules. Just like exponent rules, we have log rules. And we're going back to our pyramid of operators. Going back to our exponents. If we had a to the x blank a to the y, some kind of operator, this would be a to the x blank y, and this is a lower operator in the pyramid. Right? When we had multiplication outside, times, we had addition inside. Right? So in the exponents, when it was outside the exponent and we move it in, it goes down. For logs, it's the opposite because logs are the opposite of exponents. Okay? So we have some operator going on with the logs. Log 2 of a blank log 2 of b. I just chose 2 for some reason. Not really that relevant. But they have to have the same base, remember that? Just like when we did exponent rules, they had to have the same base. Right? Essentially, we could turn this into 2 to the a plus b, but if this was a 3, we can't do that, right? So as always, same base. It has to have the same base to apply these rules. If we put this operator inside the log, just like we put it inside the exponent, a blank b. Now a and b are inside the log. Instead of moving it down as we did the exponents, we're moving it up now. So if we add it outside, it moves up to multiplication. And that is the product rule, as you can see right here. That is this rule. I kind of did this in the reverse order. Plus, when it's plus outside, we move it up the pyramid to multiplication when it's inside. Division, if we're minusing outside, we move it up. If we're minusing, we move it up when we move it into the log. So it's divided now. I'm divided by that. Same thing here. If we have multiplication outside, some constant p, it could be like 5 or pi, whatever. If we had this constant p multiplying by this log, we're multiplying outside. We have to move it up when we go inside. So move it up to a power. So m to the p power when you're inside. Okay, so those are the first 3. That's how you can explain the first 3. And that's the best way of memorizing these rules. Okay, when you're outside and you go in, you have to move up on the ladder, move up on the pyramid. The last rule is even more important, but it doesn't depend on these. It doesn't matter for these. So you can ignore the pyramids now. They don't help you with this one, but this one's really important. So if we have the change of base rule says that if we have some kind of log base b of m, we can turn this into log base a of m, log base a of b, divided by log base a of b for any a. Why this rule is handy is that, once again, on your calculator, if you look on your calculator, if you have one handy right now, there's a log button. It's right there. The log button right there. If you click on it, it only has log, which means it's base 10 only. Your calculator can only do base 10 logs. So what if I wanted to calculate what log base 5 of 10 was? I couldn't do it on my calculator directly. I could apply the change of base rule, though. What it does is that it splits up the big number on top, small number on bottom, with any base I want. I can choose any base I want for the bottom, and this fraction is valid. As an example, if I had to find log base 5 of 10, I could turn this into log base 10 of 10 over log base 10 of 5. You have to have the same base here. I chose the base 10 because my calculator can do that. My calculator has log base 10. So if you were to plug this into your calculator, you just have to do log 10 divided by log 5. Okay? And that's how you calculate physical logs with your calculator. And you can see I took the 10 away by convention, so it's invisible again, just for the sake of freeing up some space. This one's really important. Remember, you can choose any base you want. You could convert this with the change of base rule. You could take a as pi for all I care. You could do log base pi of 10 over log base pi of 5. But that wouldn't really do much work for you. That wouldn't really help. But this is a really important strategy that you can use. You can split a log up. You can split up the base, and the big number. You can split them up. All right. You can take a screenshot of these rules if you don't have like a notebook ready or something. But we're gonna go on if there are no questions. Right. use your base log rules to simplify these logs. Okay? Simplify them as much as you can, and you can chat your answer to me when you're done. Okay, so I'm going to go over these. First one, we're adding on the outside. It's not inside the log yet. But when it goes inside, we move it up the pyramid, which means we have to multiply when we get them inside. So this is the same thing as log base 2 of 8 times 9. Log base 2 of 72. And we usually consider like one log more simplified than two logs. So that's basically the reason behind that. The next one, same thing. Outside, it's minusing. When we put it inside, it's got to divide. So it's the same thing as log base 2 of 72 divided by 8. Put that like a fraction, which is, no, not log base 2. We have to have log base 3, because it goes here. Simplify that. 72 divided by 8, that's just 9. Log base 3 of 9. Well, what's log base 3 of 9? What power do we need to apply to 3 to get to 9? 2. That's the answer. The next two, we could use the power rule. Right outside, it's multiply. If we put the 2 inside, it's got to be a power. So log base 5 of 125 squared. I don't know what 125 squared is. So you can't always rely on your rules. Sometimes you can just simplify it straight away. Log base 5 of 125, that's 3. If we multiply that by 2, we just get 6. Same thing where this one, log base 5 of 25 is just 2. Take that to the 1/2. Multiply that by 1/2, we get 1. Okay, so in some cases, the rules are good. Like this one. I don't know what log base 3 of 72 is. I don't know what log base 3 of 8 is, right? So in that case, the rules were important, but not always. So don't rely on them too much when there's better options available. Okay. kind of like a rule for anything, essentially. Now, change these logs with the change of base rule. Okay, so these should be pretty quick. Change of base rule tells us that we can split up the base and the big number into a fraction. So the big number always goes on top. I could choose any base I want for these two logs, but they have to be the same base. I'll just choose base 10 because that's what the calculator can do. If we're choosing base 10, we just don't really need to write it in because 10 is invisible. So just log 5 over log 2, that works. Oh, this one, log 2 over log 5. Just the opposite, right? So the big number goes on top, the base goes on bottom. Now I have to show that this thing is true. Log base a of b is the reciprocal of log base b of a. We can just use the change of base rule. The first one is log b over log a. The second one, the other side, is 1 over log a log b. And because of this reciprocal, this basically flips this upside down. That is true. Okay. One advanced problem here. You could call this Mathcounts level. If Mathcounts wanted to include logs, this would be Mathcounts level. So let's take a look at this one. And the factorial means that n is the same thing. 50 times 49 times 48, all the way down to times 3 times 2 times 1. Remember, that's what the factorial means. I'm almost out of time, so I'm going to go over this real quick. The trick here is that this looks really complex. There should be a way we should simplify this drastically. So we're going to apply our rules. The first thing we need to do is use change of base rule. This is log n over log 2. I'm just using log base 10 as usual, so I don't need to write in the base, just for simplicity. No. Let's take the reciprocal of each of these. So this turns into log base 2 over log 2 over log n. And it goes on and on and on and on and on. So remember now, what happens when we're adding logs? So it looks like all of these have a log base n in the denominator. Let's factor that out. So we have 1 over log n, log 2, log 3, log 4, log 5, all the way to 50. What is our addition rule? Outside, we're adding. So when we go inside, we multiply. So this is the same thing as log of 2 times 3 times 4 times 5 times 6 times 7, all the way to 50. If you notice, this number is just n, because n is 50 factorial, right? So n is right here. This is just log n. If we have log n over log n, that's just 1. And that is the answer. Okay, and that is all of that. So this is another case where you use your log rules to help you make an equation simpler so you can solve. Okay, so that's all I have for today. I'll see you next week for some more advanced topics. All right, see you later.